This example is dealing with IQ scores. Assume that adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 15. Now, when they give you those numbers, it's always good to go ahead and stop right then and possibly write it down. We know that mean, mu, is 100, standard deviation, sigma, is 15, and it turns out this is actually a pretty realistic situation. If you think about intelligences, and this of course is done on a specific test, then you know that most people, most of us, most of you, are right in the middle of being average. And so if we have our normal curve that's already on our screen, what would go in the middle? Not a 0, but a 100, because according to this, that's the average IQ. And then some people are obviously smarter than that, some people are less smart than that. And so the question says, find the probability that a randomly selected adult has an IQ greater than 131.5, which is the requirement for Mensa membership. If you're not familiar with that, Mensa is a group for geniuses. So already we know that we're going to be finding the smartest people, or the probability of finding the smartest people, and there's not going to be very many of them. So let's look at our axis. Now, we've written in symbols, we're looking for the P parentheses, X greater than 131.5. And notice that it's now an X and not a Z. Remember, we only use Z scores when it's standard normal. And obviously, since we didn't have a 0 in the middle here, it's not standard. So if we look on our graph, I'm going to go ahead and label the X-axis or the horizontal axis with X's. And since 100 is in the middle, somewhere to the right is 131. Now, if you want to actually use the standard deviation to fill in the little dashes that we have there, that's fine. I'm going to be a little bit lazy and just go somewhere off to the right and estimate. And that's really all you need to do. So if we put a dash for 131.5 to the right of the mean, and it says greater than, then we're going to go up to the graph and shade to the right for the greater than. Now, there's no way that you can have an IQ of 9,999. But remember, that's what we're using as the far right boundary. Anytime it says greater than, we don't know exactly where or how high it goes. So we're just picking that as a really big number to always use. And so if we have normal CDF, or I'm just going to abbreviate MCDF, remember the first number you type in is the lower boundary. And in this case, we're actually starting at the 131.5, so that's our lower boundary. Our upper boundary is the 9999. Statisticians like to cover all their bases, even though that's obviously ridiculously high. This time the mu is 100 and the sigma is 15. So remember, we write them in the order that we're going to type them in. Old OS calculators, you have to have that order. New OS, we have the prompts, so second vars, number 2, but we still have to type them in that order. So we had 131.5, enter, 9999, enter. Notice we actually have to type in the 100 for the mu this time and the 15 for the sigma. Paste it and enter, and we end up with 0.01786. If we're rounding to 4 decimal places, then that 8 becomes a 9, and so 0.0179 is our answer. This goes along with what we discussed earlier, that since the whole normal curve equals 1, if we only shade a tiny bit to the right, then we're only going to have a very small answer. And even though the problem doesn't ask you for a percent, think about these answers. Since they're probabilities, you can always change them into percent. We're talking a 1.79% chance that any given adult that you meet is a genius. That should make sense because most people are not geniuses, so it's a really small probability, a really small percentage. Let's try another example. The diameters of bolts produced by a certain machine are normally distributed with a mean of 0.3 and a standard deviation of 0.01. Again, I would encourage you to stop and write that down. So I'm going to put mu is 0.3. 0.30 is the same. That's up to you. And sigma is 0.01 inches. What percentage, that's a new question, what percentage of bolts will have a diameter greater than 0.32? Now again, sometimes they give this question to you in words, sometimes they give it to you in symbols. I want to remind you, they might have said P for probability, and then X, because remember it's not standard, greater than 0.32. You've got your normal curve on your screen. How are you going to label it? In the middle, we always start with the mean, which is 0.30. I like to write the letter mu to remind me. And then again, you don't have to label any other dashes, but you do need to label the number from the problem. So it said 0.32. I know that's to the right. It's larger than the mean. So I'm putting a dash somewhere estimated to the right. And then again, greater than. I'm going to go up to the graph and shade to the right. And again, greater than goes all the way to the 9999. And again, this is a weird situation because obviously you would never have a small bolt that's 9,999 inches, but that's what we're going to use as our boundary. So normal CDF, lower boundary again is on the left. Think about it as left and right, lower and upper. Upper boundary is the 9999. And then remember that your mu is 0.3 or 0.30 and sigma is 0.01. If you need to get this in your head, you might write lower, upper, mu, and sigma, although my upper looks a lot like my mu. And then we go to the calculator, normal, or second vars, sorry, number 2. And we type those numbers in. I already forgot it, hang on, 32, and we already have the 9s in there, and change that to 0.3 and 0.01. Double check your work, one little typo can mess you up, and paste to get our answer. Now I'm getting 0.0227, which is going to round up with the 5, so 0.228. But if I were to type that into the computer, I would get it wrong because remember that the question asked us for what percentage. So this time, you're not just thinking about it, you're actually doing it. Move the decimal 2 places, and you get 2.28%. I do want to point out here that as you're doing the homework, sometimes you may have a multiple choice question where the answer is very, very close. For instance, this could be 0.0226, and you're thinking, well, that's not exactly the same, but there are other ways to solve these problems besides using the graphing calculator. In the past, before the calculators, they had charts and charts of numbers. And some books still teach that. Our book actually teaches that, but we believe that the graphing calculator is more accurate and it's easier. And so if you are so close to a multiple choice answer, just consider that it was a rounding issue based on the strategy and go with it. Now, obviously, if you're further off, you may have made a mistake, but I wanted to point that out so that you can feel confident.